Welcome to the research lecture portion of the 2015 Mautner Memorial Lecture Series. This lecture, I'm Joseph Rudnick. I'm the Dean of Physical Sciences here. Some of you know me. If you don't, here I am. We are honored to present the Mautner Memorial Lecture at UCLA every 2 years. They alternate between the life sciences and the physical sciences, which means this year it's our turn, all of us in physical sciences. The Mautner Memorial Lecture at UCLA, the series was established in 1983 by Leonard Mautner to provide a forum for scientific thought and to disseminate scientific discovery to the UCLA community and the public. The inaugural lecture, by the way, was delivered by Richard Feynman, who was, as you all, I'm sure all know, was one of the great scientists of the 20th century, and he was a very close and dear friend of Leonard Mautner. I'd like to take this opportunity to thank Marguerite Mautner, who has so graciously supported and promoted the Mautner Lectures over the years. So thank you, Marguerite. We are profoundly grateful for the Mautner family's generosity in establishing the series, and we're delighted that Marguerite is here today. We are going, in fact, what I'd like to do is yield the podium to Marguerite, who is going to make a few remarks.
Thank you very much, Joe. And it's a pleasure to be here. Oh, you need the microphone. Sorry about that. I want to welcome you here today. Now, some of you have come here previously to other lectures, and some of you are newcomers. And I hope all of you will get as much enjoyment and knowledge from our speaker today, Barbara Romanowicz, who will give you a real insight into why you're here. I also want to say that I was a friend of Richard Feynman's, and the friendship started when these two young boys were 8 years old, because they decided they wanted to be scientists. So what did they do? But they fooled around and put some ointment, or what should I say, some ink on some guest towels in Mrs. Feynman's home. And when she saw the black on the towels, she got hysterical like any of us would do and say, oh my goodness, what are you doing? Well, within about 2 or 3 seconds or a few more minutes, it disappeared. And this was the first scientific experience that Richard Feynman and Leonard Mautner did at the age of 8. And after that, they were good friends, went through MIT. Richard lived in Pasadena, and we lived in the Palisades. But enough said. I am delighted that you're here, and I hope to see you again in the future. So thank you very much, Joe, and Barbara is going to do a fabulous job, as she did last night. Thank you very much.
So I'm about to yield the podium to Kevin. I just wanted to mention that last night, in conjunction with the lecture, the Mautner graduate students, 2 students were honored with the Mautner Graduate Student Award. Actually, the tradition is that only one is honored, but when the department couldn't choose between 2, Marguerite said, let's give them both an award. So thank you again for that. And I'd like to just mention them and have them stand and be recognized. They are, let me just get them right. They are Jonathan, is it? Jonathan Chang, in the back. And Igor Stubailo. Okay, Kevin, it's all yours.
Thank you, Joe. Welcome, everyone. It's my pleasure to introduce Professor Barbara Romanowicz as our 16th Distinguished Mautner Lecturer. Dr. Romanowicz is a professor of geophysics at UC Berkeley, and she is also chair of the physics of the Earth's interior at the Collège de France In fact, she currently splits her time between Berkeley and Paris, which sounds nice, but may be a bit challenging from time to time. A lot of frequent flyer miles, perhaps. As I'm sure most of you know, Barbara is internationally recognized for her contributions to the fields of geology and geophysics, and is widely regarded for her studies on the architecture of the deep earth, as well as on earthquake processes. She received her undergraduate degree in mathematics from the École Normale Supérieure in Paris, and she went on to receive a master's in applied physics from Harvard and completed doctoral degrees in both astronomy and geophysics at the University of Paris. After a postdoc at MIT, she returned to the Institute of the Physics of the Earth to assume the position of the Director of Research and the Director of the Geoscope program. She's been on the faculty at UC Berkeley since 1991, where she served as director of the Berkeley Seismological Lab for 20 years until 2011, I think. So Barbara has garnered many accolades and honors in her distinguished career. A few highlights include the silver medal from the French National Academy of Sciences, the Wegener Medal from the European Union of Geosciences, the Inga Lehman Medal from the AGU, and the Harry F. Reed Medal of the Seismological Society of America. She's a member of the National Academy of Sciences of the United States and a Chevalier de la Légion d'honneur de France, an order established by none other than Napoleon Bonaparte in 1802. And I understand it comes with a very nice medal and ribbon, but no horse, not to my knowledge anyway. So please join me in welcoming Dr. Barbara Romanowicz, who will speak to us on mantle plumes and secondary scale convection, recent insights from whole mantle seismic waveform tomography. Barbara?
Okay, good afternoon. Can you hear me? Okay, so thank you very much, Kevin, for this nice introduction. Thank you, Joe, for having me here, and Marguerite for making this possible. And so today I will talk about some recent work that we've been doing on mantle tomography. And first, I'd like to make sure I acknowledge my students who've been working with me, and without whom the results that you will see would not have been possible. So very recent graduates, Scott French, Ved Lekitz, and Sanne Cotter, whose results I'm going to be talking about. So let's start with 30 years of tomography. This model here, I'm showing maps of shear velocity at 100 kilometers depth in the mantle. On the top is the first tomographic model on that scale, which was constructed by Woodhouse and Jablonski in 1984, so 30-some years ago. And at the bottom is a recent version of the same kind of tomography. And I'm showing this to indicate that both things have changed a lot and not that much. Already in 1984, the main units visible in the structure of the Earth's mantle were there. You could see this, so red means slower than average, so hotter than average. This is wave propagation velocities. As earthquake waves propagate through the medium, they travel faster or slower. They are slowed down when they go through hotter regions and sped up when they go through faster regions. To first order, that is all you need to remember. And you can see the slow, where than average, hot ridge system. You can see the back arcs here, also slow. You can see the cold cores of the continents, and you can also see the cooling of the Pacific plate here as it ages towards the west. All these elements were already present and reflected very nicely, sort of showed a kind of confirmation in a way of plate tectonics. More recent models show more details, but at least at this depth, they basically confirm the features that were already available at that time. And the whole point of what we're trying to do in seismic tomography and imaging the Earth's interior at the global scale is to get better and better resolution, to see finer and finer details to try to understand better how, to provide better constraints on how the Earth works, how mantle dynamics works. So this image shows good correlation with plate tectonics. There are, however, observations, geophysical observations in the oceans that have been puzzling for a long time. This, for example, is the heat flow measurements as a function of the age of the oceanic plate here in millions of years. As you go away from the ridge, the heat flow kind of decreases in a way that, in a simple model of a half-space cooling model, should be as a square root of the age of the plate, of time. In fact, beyond about 80 million years, you see a flattening in this curve. Same thing for the bathymetry, the topography of the ocean floor. It should be decreasing also as a function of square root of age, but it flattens for old ages. And in order to explain this, you have to introduce some way of bringing heat to the middle, to the bottom of the plates in the middle. And so one way to do this is to introduce the so-called plate model, which was introduced around the same time, which is one way of providing constant supply of heat from below. But so what is this heat? What are the mechanisms that can supply this heat? So two mechanisms have been proposed for delivering heat from deep in the mantle. One is through hotspot plumes, which would be anchored at some boundary layer deep in the mantle and would provide hot upwellings, narrow upwellings that would be fixed with respect to the motion of the plates at the surface. This is a hypothesis first proposed by Morgan and then elaborated later on over the decades to kind of account for the interaction of these plumes with the motions of the plates through the asthenosphere system. The other hypothesis that was proposed on the basis of experimental and numerical computations of convection was that of the Richter rolls, where upon the effect of moving plates, here you have plates sort of moving apart at the ocean ridge. And as time progresses, the motion of the plate over the overlying mantle, over the overlying asthenosphere, causes the formation of these convection rolls, which ultimately align in the direction of the plate motion. And many years, for many decades, geophysicists and in particular seismologists have been trying to see or to image and find any evidence in the mantle of these plumes. And I should say it's not only seismologists, but also other types of geophysicists. So I'm going to show some recent results in mantle tomography. So to introduce this, this is a seismogram, a typical seismogram, which contains a rich variety of energy arrivals as a function of time. This is for a large earthquake observed at a large distance of about 10,000 kilometers. And most tomographic models until now relied on the measurements of travel times of very specific phases. So here, the first arriving P phase, the second arriving S wave, the SS wave, which bounces one from inside on the surface of the Earth, and then the surface wave trains. These phases are well isolated in the seismogram. It's relatively straightforward to measure their arrival time and then relate that to the structure. But in fact, that information is limited, and there is much more information inside a seismogram. Here, what I'm showing, this big kind of chart here, is as a function of distance from the source to the receiver, the arrival times of many identified seismic type of waves, which you call phases, which interact in various ways with the internal structure, the main units inside the Earth. And you can see that the P wave here, for example, arrives isolated, so you can measure it separated from the rest. But as you go into this region, for example, there are many waves that arrive at the same time. Each of them samples a different part of the mantle. And these waves would not be considered in this type of models. In order to be able to consider them, you really have to try and look at the seismogram in its entireness, the whole seismogram, the whole waveform. And so in my group, we've been developing methods actually for a long time now, for about 20 years, where we try to model, to improve our models by comparing an observed seismogram, like here, with what we call a synthetic seismogram, which is the predicted wave field, seismic wave field, in a particular Earth model, an Earth model that would have some complexities inside it, which are the ones that we are trying to determine. And the issue here is, how do you compute a synthetic? So we know how to compute a relatively long period synthetic in a 1D Earth. By 1D, I mean a spherically symmetric Earth, using the so-called normal mode theory. Normal mode theory is basically the idea that any displacement on the Earth's surface can be represented as a sum over the normal modes of the Earth, or the normal vibrations of the Earth. And we know how to calculate that very well in a model of the Earth made of spherical shells. The Earth is actually three-dimensional, and so and we are interested in these departures from the spherical symmetry. And so to do this, we also know how to do that in the framework of normal mode theory by using so-called perturbation theory. However, this is an approximation. We've developed methods to do this over the years using this normal mode perturbation theory. A challenge is to model the body waves, the waves that travel through the inside of the Earth. It's somewhat easier to model the surface waves in this method, but we've introduced some ways to capture the sensitivity of the body waves to the actual structure. So here I'm showing the cross sections of the Earth, and these are sensitivity of different waves, and you can see here that a body wave will be more sensitive to the ray path, and in the kind of ray theoretical approximation, it will be sensitive to the infinitesimal ray path between the source and the station. This is for an SS wave, S and S here. This is for an S diffracted. On the other end of the spectrum, you have surface waves, which are primarily sensitive to the average 1D structure, as indicated here by these shades of gray between the source and the receiver. But in fact, if you look at a full seismogram, you have a so-called finite frequency effect, which is the fact that the waves are actually sensitive, not only, the body waves are sensitive not only to the structure right beneath the ray path, but also to some width. And also the sensitivity depends on the position along the ray path, which is illustrated here. So for many years, we kind of developed models based on this type of approach, but already taking the whole seismogram into account. And in this slide, I'm just illustrating how, these are three models, still at 100 kilometers depth, I believe, of shear velocity variations in the world. So you recognize now the patterns. They're very similar between each other. The difference is that these two models use combinations of data which are in particular based on these travel times of waves, whereas the middle one is based only on the waveforms. This is the one. And you can see that at least here we're showing that this waveform formulation allows you, with a relatively small number of seismograms, to obtain more or less the same resolution as you can obtain with these more classical methods. So extending this to the lower mantle, we also have kind of sort of proven the idea that you can do this with waveforms. Here are 5 models that have been obtained using mostly travel times of a limited number of seismic waves, and this one has been obtained using full waveforms. And again, the similarity of the models, at least at the long wavelengths, is quite striking. In fact, today, the agreement between different tomographic models obtained using different methods are really quite good at the base of the mantle and bring out the first order structure, which is two large regions of lower than average shear velocity surrounded by a ring around the Pacific Ocean of fast velocities. This plot is a little complicated. It's counting how many among the 5 models think that the velocity is lower than average and how many think they're faster than average. If they all agree, it's either dark blue for the fast region. If they all agree that they're slow, it's red. And you can see that the agreement is this map comes out very bimodal, and not only do they agree on the general pattern, but also on the actual shape of the borders of these two regions, which have a lot of similarities. They are antipodal and centered on the equator, but the shapes are rather different. So, so moving on to more kind of recent approaches, in the last few years, so the perturbation theory has been very helpful. However, it's still an approximation, and you need to assume that the model, lateral variations in the model are weak and relatively long wavelengths. The strength of the heterogeneity is weak, and the velocity variations are long wavelengths. We know that this isn't quite true in the uppermost part of the mantle, and also near the core mantle boundary, and perhaps also in some areas in the mid-mantle. So we need to have a better way to predict the wave field generated in these more complex models. And this has been possible for the last few years by the fact that there are now very accurate numerical codes that allow us to compute the seismic wave field, so the propagation of the waves and their interaction with the heterogeneity through rather arbitrary complex media. And one of the favorite methods that is really well applicable to the global spherical case in the Earth is the so-called spectral element method. So now we can compare the data, the waveforms in the data, to this much more accurate kind of way of computing the synthetics. And what that buys us is that now we are freed from any assumptions on the heterogeneities, and in particular, we will have better kind of resolution. I really insist on this on low velocity regions. The way of limited extent. The way it works is that if you have a wave going through a low velocity region, what you pick up at the other side, the first wave is going to be actually not going through the region, but it's going to go around because it's going to go through the region that is faster. So slow velocity regions are actually hidden from view if you only look at a very small portion of a particular wave, like the arrival time. In order to really capture the full effect and see this feature, you really need to look in a broader band sense and look at the waveform, the complete wave field. And okay, so numerical methods can help you do this. However, there are challenges because these are heavy computationally. The computation time increases as the frequency to the power 3. So if you want to go to finer and finer details as you increase in frequency, this becomes quite difficult computationally. You need several hundreds of earthquakes sources of events. You need several iterations because this is a very nonlinear problem. And there are other issues such as the presence of thin, slow layers in the Earth's crust, which also slow down the computations. I think I will skip this slide, which was meant to illustrate how a low-velocity anomaly interacts with waves that actually don't necessarily pass through it. And these are on top of each other seismograms with and without this kind of, actually it's a column, circular column in the middle of the Pacific here. and they're on top of each other, you don't see much of a difference. You start seeing it appear in sort of the coda of the different waves, and this is the difference between the two, which has been multiplied by 3. But however, these differences is what we can now interpret more fully. I won't go into the details of the method. We use the spectral element method to compute the forward part of the model, of the modeling, and then for the construction of the tomographic model, we have an inverse part, which we actually compute approximately using these kernels based on normal mode perturbation theory, which allow us to use a Gauss-Newton fast converging inversion scheme, and so speeds up the computations while allowing us to obtain a model in a reasonable time. So far we've developed 3 generations of mantle shear velocity models using this approach, spectral element method, 2 generations of upper mantle models, upper mantle by mean down to about 800 kilometers, and a recent whole mantle model where in these upper mantle models, we've gone down only to 60 seconds period, so these are very long period data. And in the whole mantle model, we've added waveforms, body waveforms, so waveforms of waves going through the mantle down to 32 seconds. And I will be showing some of these results. So first, I want to illustrate why we think we're getting better constraints on, that we actually are getting better constraints on the low velocity zones. This is, again, a map. This is at 70 kilometers depth. You recognize the ridge system here. And I'm going to show comparisons of models that were obtained at the global scale with a model that was obtained locally, because there was an OBS experiment here in this region by the group in Brown University, from which they derived a local model which serves as a reference. So these is the local model is here. So these are just profiles of the average shear velocity destruction as a function of depth here from 50 to 350 kilometers depth. This is shear velocity in kilometers per second. Sorry, the labels are missing. The yellow here is the local model. What it shows is this minimum in the velocity occurring around 90 to 100 kilometers depth, which is a well-known feature. But the important point here is that the shear velocities are very low. They reach about 4 kilometers per second. These are 2 recent tomographic models developed using more standard approaches based on normal mode perturbation theory and ray theory. And you can see that they show the presence of the minimum at about the right depths, or the same depths. However, they fail to capture the strength of this low velocity zone. Now, with our latest model, we are actually able to match the local absolute velocity much better in this region. And this is, of course, important because the tomographic models are only one step towards understanding what happens in the Earth. You get the distribution of these elastic parameters, the shear velocity here specifically, and then you want to interpret it in terms of what it means in terms of temperature and composition. And in order to do this interpretation, you really have to have good constraints on the absolute velocities. So this is just a local comparison, sort of a reference point, but then we can now extend this along the whole East Pacific rise, where we don't have the local measurements, but you can see these depth cross-sections. This is the velocity, and this is the corresponding radial anisotropic parameter. I won't talk too much about this here, but you can see this low velocity zone with its minimum kind of more or less constant along the ridge, with some fluctuations, but with also a quite well-defined base below which the velocity variations are much less strong. Now, if we look, this is along the ridge. Now we're going to look across the Pacific, and we're going to look at a comparison. Here, the cross-section, depth cross-section that I'm showing here is in the Southern Pacific here. This is S40RTS. It's a recent model by Ritsema et al. Showing what the black dots show here are the seismicity here in the Western Pacific, and this is the South American subduction zone here. And you can see from this plot the general pattern, long wave and pattern, where you can see the low velocity zone here quite marked in the first 150 kilometers. You can sort of see the difference between the lower than average velocity zone, velocity in the Central Pacific and elsewhere. So now I'm going to compare this with our recent upper mantle model, which shows very much the same features, but now much more kind of sharp. And in particular, we can resolve the subduction zones much better, these blue zones here, colder than average. And in the Pacific, we can resolve these features that appear as columns. They're not mixed together like here, even though the background is very compatible, but they appear as kind of separate zones. And they correspond more or less to the zone of the South Pacific superswell, these hotspot volcanoes here that are more or less labeled. I would note here, this is a comparison with a local tomography in the Tonga subduction zone, where you can see the agreement where the subduction zone is going down and then it flattens somewhere around the 660 kilometer discontinuity. This feature is also actually visible in this model. So now I'm going to show some pictures of this area, but in 3D. I showed those yesterday already, where we're looking here from the south, but in a 3D sense. These are the superswell volcanoes, Hawaii, Samoa. And what I want to point out here is the difference between what you see in the structure in the first 300 kilometers, where things are elongated in the horizontal direction. You see the low velocity zone here, the ridge is somewhere here, so the low velocity zone peters out as we go towards the western Pacific, towards the older oceans. But there is also another zone here of elongated structure, low velocity structure centered around 250 kilometers that we will see better in the next slide. Note that below this zone, the structure changes its kind of appearance, and we see these white columns that are vertically oriented and separated from each other and may be associated with some of these hotspot volcanoes. If I turn this around and now look from the east, I see this structure difference again, but now I'm seeing these features around 250 kilometers as they appear as kind of low velocity, regularly spaced low velocity zones that in fact are elongated in the direction of the plate motion. And below that you see these columns, in particular one associated with Hawaii that is kind of meandering through the upper mantle. So let's first discuss these features here. This is below the low velocity zone, and I'm going to now show some 2D cross sections across the Pacific in the direction perpendicular to the direction of absolute plate motion of the Pacific plate. Here I'm showing the map at 250 kilometers depth. Sorry, that went away, that label, which is shown as just variations from the mean, right? So the red shows slower than average, blue shows faster than average. Here are these three cross sections, 1, 2, 3, showing the same model, but now in absolute velocities, so 4.2 to 4.8 kilometers per second, just to show the relationship with depth of the velocities. And you can see these quasi-periodic features in all these cross-sections, separated by about 2,000 kilometers horizontally, that extend down to about 300 kilometers, at least in these slides, and where the velocity is as low at 250 kilometers within one of these, what we call fingers, and as it is in the low velocity zone between the fingers. So these features are really quite striking by two facts. First of all, they're quasi-periodic in their position, and they are elongated. You see these things in the direction of plate motion. So now if I look at this globally, this is a map of the model at 250 kilometers depth. And what I'm going to put on top of it are lines that are not arbitrary. They are plotted in the direction of absolute plate motion. And I've plotted them on top of, sort of to coincide with some points that are on these low velocity features. But you can see that these elongated zones are indeed aligned in the direction of plate motions. They're separated by about 2,000 kilometers, and they are there not only in the Pacific plate, but also in other places. You can see them in the Antarctic plate. You can see them also in the Indian Ocean and in the Atlantic Ocean as well. And I will get back to this later. But the next thing I will show is that this signal actually seems to correspond quite well to a signal that's present in the Earth's geoid, so in the gravity field. This is a comparison of our map at 250 kilometers depth. And this is a directional wavelet analysis of the Earth's geoid, which is showing here for particular directions which are close to the direction of absolute plate motion would be those pink colors. There is a maximum of energy in the geoid at about a wavelength of 1,800 to 2,000 kilometers. And this is a representation of this particular features in the geoid, which, and the black lines are the same as those that were plotted here in the direction of absolute plate motion in the Pacific. And interestingly, the wavelength is the same, but the maximum strength in the geoid occurs in between the minima of our velocity features. So right now we're trying to understand this relationship from the dynamic point of view. Just a moment in the Indian Ocean, so this is a zoom in on the Indian Ocean where we see these elongated features in the upper mantle. On top of it, the absolute plate motion paths. And I'm showing this to show that these features that we see in the mantle in tomography actually correspond to some active process, current active dynamic processes. The way I show this is by comparing this to the hotspot tracks in the Indian Ocean. Here is the Reunion hotspot track separated by the Rage, and then continuing here and going over to the west of India, whereas our corresponding here channel or finger starts here, is offset by the Rage, but then continues to the right of the or to the east of India. And so you can see that our fingers are really showing the direction of current plate motion, whereas the hotspot tracks are showing the kind of manifesting the change in the orientation of plate motions around here, maybe 45 to 50 million years. The same happens on the 90 East Ridge. You can follow the, we have this finger here that goes like this. You can follow the hotspot track here, and then it goes further northerly, whereas our finger continues in the present-day plate motion. So, okay, so what are these features? There are two kind of ideas that come to mind. One is based on experiments of so-called viscous fingering experiments. If you include a low viscosity fluid into a layer of higher viscosity, mu is here viscosity, that is between two plates, the lower viscosity fluid will spread, forming this kind of flower features with the petals organized in a sort of periodic fashion, and the periodicity depends on the thickness of the layer, the viscosity contrasts, etc. If you impose a motion to the upper boundary, so you have a mobile plate on top, these fingers will align in the direction of plate motion, both in the direction of plate motion and in the direction opposite to plate motion. So this kind of is reminiscent of what we're seeing, but as I mentioned at the beginning of the talk, there is also this idea of these Richter rolls, the secondary scale convection. So in reality, perhaps what we are seeing is a combination of two things. Low viscosity fluid, so this is looking along one finger with the low velocity going down to 300 kilometers here, the low velocity zone, and this is perpendicular to it with the periodicity. And this kind of gives us this idea of fingering, right, in the horizontal direction, kind of imposed by the plate motion. And this one here we might be having also manifestation of secondary scale convection in the upper mantle. So now let's move on for a little bit to what we see deeper. I'm going to talk about the latest results on the whole mantle parts. So just to remind you, we've seen this. This is the upper mantle part. When we add to lower mantle parts to this model, it doesn't change that much. And the question is, what do we see below? How deep are these columns anchored? So we're looking, this is a view of them from the top. We've cut out everything above 500 kilometers. So we're looking like if we put the top boundary here at 500 kilometers and looking deeper. And you can see that these columns are quite well spatially associated, at least to first order, with some of the individual hotspots here, Hawaii, and then Samoa, and the superswell volcanoes. So what I'm going to show in the next slides are some cross-sections in the Pacific across these features. And so first, I'm showing some 2D cross-sections here across the Pacific superswell region. And the cross-section, the direction of the depth cross-sections are indicated here on these little maps. So this one goes right north-south through Samoa. And you can, and then this one goes east-west. This one goes slightly northerly, going through Pitcairn. And this one goes through McDonald. And so in each of these cross-sections, what's very striking are these columns of significantly lower shear velocity than average that extend from the core mantle boundary to at least about 1,000 kilometers below the surface. They are quite wide. They're, as seen here, about 1,000 kilometers wide. We will return to this issue. But you will notice that these cross-sections span half of the world. And they are very distinct features in these cross-sections. They're unique. There's no other such feature in these cross-sections. Here you can see 3 of them. These correspond to some of the plots that I was showing you in the upper mantle earlier, but you can see them as rather well-separated features all the way down. You see McDonald, which is somewhat offset from the location of the actual hotspot at the surface of the Earth. And in Pitcairn, which is also slightly offset, we see, note this kind of rolls or alternating zones of high and low velocities in the upper mantle, which in this model actually seem to extend a little deeper, perhaps all through the upper mantle down to 660 kilometers. What I want to show you is that this is not, these are not artifacts of the inversion. If we actually compare this model to recent other models, this is our model here at the top for McDonald, for the cross sections crossing McDonald and Pitcairn, and this is the same cross sections, but in the Ritzema et al. Models 2011 S40RTS. If you compare these two, you can see pretty much very similar features. You can already see in this model sort of an outline of this feature, except that if you're only looking at this model, you might argue that, well, we don't really know whether this is continuous. There's these other features here, so this isn't quite well established. I think with this model, we really are establishing that there is a continuity of these features, quasi-vertical, very vertical in the lower mantle, and ending up sort of in the vicinity of these hotspot volcanoes. Note that on this cross-section we have here, we're going also in the vicinity of Yellowstone, but we don't see Yellowstone in the lower mantle. Or maybe this very faint feature here might be related to Yellowstone. In any way, whatever it is, it's very different in nature from what we see under these superswell volcanoes. This is a comparison. Here I've replaced it by the Princeton model, which is one of the models that kind of proposed the existence of plumes throughout the mantle. And again, there are some similar features like this offset of McDonald, but this model, which was very controversial, didn't really have the continuity of features throughout the mantle. So we can go down, so superswell, I showed this yesterday, from the superswell region, seeing these columnar features and how they continue down in depth. So this is at 400 kilometers. It sort of looks almost like a model of convection, a 3D model of convection. But you can see that at this depth, they're already starting to kind of spread horizontally. If you go deeper, they're more focused as vertical individual columns. As you go deeper, you see that continues until you get close to the core mantle boundary. Around here, I'm already 150 kilometers above the core mantle boundary. And here the structure kind of mingles or kind of is combined into these large low shear velocity provinces. I want to spend a moment talking about Hawaii, which is the topic of a lot of discussion of what is the, how deep is the Hawaiian plume. In our model, the Hawaiian plume is pretty vertical. It's in the lower mantle, and it also is anchored in a patch here of very low velocity zones at the base of the mantle. This is a 3D rendering from the southeast, showing how this columnar structure interacts with one of these fingers that is going through in the vicinity of Hawaii, this red zone. So this is a rendering showing mostly the lower than average, significantly lower than average velocities or significantly higher than average velocities. We see these features also in the Atlantic. These are cross sections, again, going half of the world around. This is near the Cape Verde hotspot. Again, a feature anchored at the base of the mantle, going up all the way at least 1,000 kilometers. This line here is about 1,000 kilometers. This is Canary. Again, a feature going straight up from a very low velocity patch at the base of the mantle up to at least 1,000 kilometers, and then things kind of either disappear or get deflected, like here in St. Helena, for example. The Iceland hotspot is not as strong, but is still visible. I guess the important features that you see here is this continuity, vertical continuity of these features that are, all of them kind of can be associated with a particular hotspot, not necessarily right above it. You can see the continuity up to 1,000 kilometers. Then things get a little more complicated. There's deflections. I'll get back to it. And probably these features become thinner, which is what you would expect as you go from a higher viscosity lower mantle to a lower viscosity part in the upper mantle. I would like to stop for a moment on the very base of the mantle. The very base of the mantle, where we know from our classical kind of tomography that we have these large low shear velocity provinces. If we filter our model here to, well, this is spherical harmonic degree 12, we see that we have features in our model that are very compatible with those of other models. This is the Harvard model S362 ANI. And this is a comparison with this model that I've been making comparisons with S40 RTS. So if I was to plot this model in the same way as I did counting where is low and where is fast, this model would be quite compatible with these previous models. But now we're seeing more features at this depth. And so this is the complete model. So not filtered to just long wavelengths, but also with its short wavelengths included. And on this, what I've plotted here are the locations of these large fat plumes that we're seeing, and the black ones are the ones that are really very clearly seen all the way from the core mantle boundary to the at least 1,000 kilometers depth. The gray ones are somewhat weaker, but still very clearly resolved. And then there's a few here white ones that we think are also resolved, but they're a little bit more questionable. There's only one of those that is not associated with a known hotspot. And the other remarkable thing is they are all located within the LLSVPs, within these large low shear velocity provinces. These other dots, the green ones in particular here, Yellowstone and others, are other hotspots that have been documented in the literature and of interest, but they are not located inside the LLSVPs, and we do not see any such strong features associated with them in the lower mantle. Going back to Hawaii, I showed you, Hawaii here is anchored in a patch of lower than average velocity. It turns out that one of my students, Anna Cotter, thesis was, she did some forward modeling, so looking at observed waveforms and trying to match them with a model that would explain them. But she looked at diffracted waves on the core mantle boundary between events in the Western Pacific and the US array here in North America. So the green here lines indicate the path in the last 300 kilometers of the mantle near the core mantle boundary. And the purpose of the study was to study the borders of the large low shear velocity provinces, which are in some areas have been shown to be sharp. In fact, the observations that we found were quite remarkable. So as a function of azimuth, as the path is going further southerly, we see these waveforms. This is the main diffracted wave, which kind of disappears. And instead of it, you see a much delayed, what we call a post-cursor here appear. This is a prediction from this tomographic model, which is an old tomographic model, but pretty decent one. And all you see is a slight delay as you enter the slow velocity zones, but there is no reduction in amplitude and no post-cursor. In order to explain this, in order to match these data, you actually have to introduce a very strong structure here located a little bit southwest of Hawaii, which is one of these ultra-low velocity zones, what we call an ultra-low velocity zone. It's a feature that, and of course there's some non-uniqueness in this model. This is a very simple cylinder with height of about 25 kilometers, diameter 800 kilometers, but a velocity reduction of 20%, right? In the tomographic models, in particular the last one I've shown, the velocity reduction is still a few percent. It's still 2 to 4 to 5%. This is much larger. So this is a very remarkable feature, and it is the bending of the rays and interaction with the feature that causes these the reduction in the amplitude of the main phase and the appearance of the post-cursors. And it turns out that when we wrote this paper, we couldn't really say, this was sort of close to Hawaii, but there was some uncertainty in the exact location, and there was no way to, except by outward speculation, to associate this with the Hawaiian hotspot. But with the now with the tomography, the location of this spot is right where we see this patch of reduced velocity. So we are thinking now that this patch of low velocity that is seen in the tomographic model actually contains an ultra-low velocity zone, and that in fact it's not this is not the only one, but here under Samoa, which actually happens to be on the same cross-section, we also have such a patch, and there has been a recent study by Thorne et al., which has provided evidence for the presence of an ultra-low velocity zone. Another of these kind of plume and hotspot associations is in Iceland, where there has also been some evidence for the presence of an ultra-low velocity zone beneath the hotspot on the core mantle boundary. So what are these kind of plume-like features? We have learned from geodynamic experiments that we expect to see thermal plumes in a fluid heated from below. But the classical picture is that these plumes in the Earth's mantle should be rather thin. They should be no more than about 200 kilometers thick. Ours are much wider, and I'm going to make an argument in the next slide for why we think they have to be that wide. And they also show some kind of variations in their shape with depths. And so they kind of remind us of geodynamical experiments where, in fact, these plumes would be derived from a layer of different composition at the base of the mantle, which would partially entrain some material, and in which, in this situation, you might get much fatter plumes, but this may not be the only explanation. However, our plumes are definitely fatter. So this is a synthetic experiment where we input a plume which is here from the core mantle boundary to 1,000 kilometers depth, and it's 400 kilometers in diameter. And we pass it through the last iteration of our inversion, which is what we can do in a reasonable amount of time. And this is what comes out. So the plume is here 2% slower than average, and it comes out somewhat wider, but about 1.5, less 0.5% velocity. If you remember, our plumes were about 2% velocity reduction, but much wider. So in this test, you can multiply the strength of the plume to get what you get out, because it's a sort of a linear test. And so in order to get 2% velocity output, you need to multiply this by about 4, right, the strength. So the initial velocity in the reduction in the plume would have to be 8%. And if you translate that into temperature, this provides excesses of temperatures in the plumes, which would be at least 1,200, if not 1,500 degrees contrast, which seems quite unrealistic. So this is not a direct argument, but it does indicate that for reasonable excess temperatures, in order to see those plumes, they have to actually be fat. I mean, maybe not as fat as we see them, but much fatter than 400 kilometers. The other thing I wanted to go back to is what we see happening at 1,000 kilometers. We see this change, these sometimes deflections, like you see in these cases. Sometimes they kind of disappear, and that doesn't mean they don't exist. It means that we lose resolution in the upper mantle because they might be thinner, and therefore we can't see them at the resolution at which we have now. But this is quite striking that something seems to happen somewhere around 1,000 kilometers depth that looks like deflection from, for example, this model by Farnantani and Samuel, where this model was with a transition viscosity at around 660 kilometers, with a plume coming up, a thermochemical plume, and being deflected and thinned as it goes to the lower viscosity upper mantle. I would like to point out that in subduction zones, we see also something going on around 1,000 kilometers. These are from a recent paper by Fukao and Obayashi, 2013, showing subduction zones here in the Fiji, Tonga, and Kermadec, cross-sections along these different lines, showing the slab. The seismicity is shown in white. And in these particular areas, at least in the Tonga region, you see some kind of slab flattening at 660, but then also a big portion of the slab going deeper and flattening horizontally above about a level of 1,000 kilometers. In Kermadec, the slab actually goes all the way through the 660 and flattens above 1,000 kilometers. So this makes us, we are seeing something going on both in fast regions, in regions of subduction, and in regions of upwellings at about 1,000 kilometers. There is no evidence so far for any physical process that goes on at 1,000 kilometers. There's no known phase change or any obvious reason why this should happen, but this is quite clear. And if you do try to see how correlated the structure is above 1,000 kilometers and below, you see very clearly a decorrelation at the global scale and at the long wavelengths between what's above this level and below, and not only in our model, but in many other models. So to conclude the findings here, primarily in the upper mantle, we now see these low velocity channels that have a horizontal wavelength about 1,800 to 2,000 kilometers. They're ubiquitous under ocean basins. They're aligned with absolute plate motion. And they extend from the low velocity zone through perhaps all the way through the transition zone, as shown in our latest fully whole mantle models. And below that, we see these individual plume conduits in the vicinity of major hotspots. They're rooted in D double prime, all of them. Some of them we know are associated with the presence of large ULVZs at the base of the mantle. They're fat in the lower mantle. The diameter has to be really large in order for us to be able to see them. We're improving our resolution as we go, but we're still somewhat limited. The plume conduits are quasi-vertical from the core mantle boundary to about 1,000 kilometers depth, where they start deflecting and maybe thinning. And so above 1,000 kilometers, they may be thinner, and they're undulating, as you saw in the, for example, Hawaii, in the upper mantle 3D pictures. And they seem to be interacting with a secondary scale convection in the upper mantle. And one last point, the hotspots are offset from their origin in D double prime. So the concept of a hotspot, with a directly vertical plume underneath it all the way to the core mantle boundary has to be also somewhat modified. So I think I'll stop here. Thank you.